Yesterday we introduced the Kerr metric, talked about how to an event horizon and an ergosphere. And in the ergosphere, our killing vector, which is time-like at infinity, actually becomes space-like. And the ergosphere is also the region where time-like observers actually have to rotate with the black hole. So today we're going to talk about geodesics on the Kerr spacetime. So these geodesics, not only determine the trajectories that small test bodies have to follow around spinning black holes, but they'll actually give us some important intuition even for the non-test body case. For example, binary black hole mergers or things like that. So I'll mention a couple of those types of things at the end of the lecture. So so geodesics. So as a reminder, the geodesic equation is just given by this equation, where here u is the forward velocity, so it's the derivative of the spatial coordinates with respect to some affine parameter, and usually for time-like observers, we take this affine parameter just to be the proper time. And with that choice, our time-like forward velocities satisfy this normalization constraint. These were instead null geodesics, then this would just be 0. So in a generic setting, this equation would actually give us a second-order equation for the position of the particle. We just write it out. It would be this, so it involves second derivatives of the position with respect to proper time. So, of course, we can still calculate this, but we'd have to integrate these second-order equations for a generic spacetime. However, for the Kerr spacetime, we have conserved quantities. And we know that we have conserved quantities because we have killing vectors. So in particular, these conserved quantities will be constant along geodesics. So the first constant we'll just get by contracting our time-like killing vector. And just remember, this is just the one that in our Boyer-Linquist coordinates just looks like this. And then our axial killing vector is the one that just has a 1 for the phi component, the phi component when we have upper indices. So if we contract that with our forward velocity, we just get minus e with a lower t. The minus sign is so that this quantity will actually be positive, and the tilde over the e, so this is energy, but it's actually the energy divided by the rest mass of the particle. So if I had contracted with the forward momentum instead of the forward velocity, I would actually get energy. But since we've divided by the mass of the particle, this is the energy normalized by the mass. And then, of course, we can do the same thing with our axial killing vector. And then again, we get this angular momentum per the mass of the particle. So we can expand this out. So if I want to raise the index back up, there's only the tt and the t phi component, and then writing this out. And similarly for the angular momentum, okay, and we'll remember these expressions from yesterday, the sigma and delta. So just to remember, delta here is just r squared plus a squared minus 2mr, and sigma is r squared plus a squared cosine squared theta. Yeah, so we have energy and angular momentum, and we'll notice that if we go to very large r, so then this just becomes an r squared, and we consider a particle that has zero velocity, then this this energy just goes to 1. So a marginally bound particle that has zero velocity infinity will just have E equals to 1. So that's the rest mass contribution to the particle. So far we have these two constants. So for generic Kerr orbits, there actually turns out to be another constant in addition to these, and then of course the normalization, which you can also think of as giving you a constant. And that just comes from the killing tensor that I mentioned yesterday. So with this killing tensor, you can actually define another constant, which is called the Carter constant, by contracting our geodesics with it. But we're not going to talk that much about this because basically this constant allows you to integrate generic non-equatorial orbits. So in Kerr, if I start with the generic orbit, it's not necessarily going to remain in one plane. It can process and map out different planes. However, for the rest of this lecture, we're going to instead concentrate on just the equatorial case. That is where theta is equal to pi over 2. And in that case, the Carter constant just tells us that if we start with no velocity in the theta direction, then we can remain in the equatorial plane. So for that special case of equatorial orbits, they are confined to this plane. Yeah.
So all of the energy and the angular momentum we get from contracting killing vectors with geodesics. So those do have like a Newtonian analog in terms of energy and angular momentum. Do we have a Newtonian analog for C?
No, not really. Because, yeah, I mean, it's basically just due to the spin of the black hole that you get this effect where you don't sort of have a fixed orbital plane. So it really is kind of a relativistic thing. Okay. So I think in the Schwarzschild limit, this becomes something like just the angular momentum in the z direction squared or something like that. So I mean, it will reduce to something, but it's not an extra constant. Yeah. Yeah, so the Carter constant is still a little bit mysterious. Yeah, good question. Yeah, so from now on, we'll just stay to the equatorial plane. And it turns out there's lots of interesting phenomena that happen just with this restriction. All right, so So instead of working from this equation, let's just start from here and use these constants. Okay, so just actually starting with upper indices here on the metric and lower indices here, can just expand this out. These are the non-zero terms. And then we can replace the lower UTs and the lower UPhis just with the constants. And we get a minus sign here because of the minus sign I defined over there. And basically, the only one we have left is the forward velocity with the lower r component. And that's related to the one with the upper indice, of course, just by this expression, since this is the only non-zero r metric component, and that's just this. Okay. And these, of course, are just the components, the inverse metric. So to calculate them, we just take the metric, consider it a matrix, and do matrix inversion. So just go ahead and write those down. And using the fact that we're restricting to theta equals pi over 2. Okay. So let's call this equation star, and we can rewrite star using this. Okay. So a little bit simpler. Now, just want to do a little bit of algebra. So we'll move this guy to the left-hand side, move this guy to the right-hand side, and multiply through by delta r squared. And let's call this equation double star. And finally, we just want to collect the different powers of r. So the leading term is going to be r to the fourth. And yeah, and here we're using the definition of delta we have up there. We're going to call this whole thing V. So you notice on the right-hand side, we basically have something that's like negative times dr d tau squared. And then this term is going to go from that kind of like r to the fourth. So this is essentially the effective potential for our radial motion. And you'll notice that, because I said this goes like r to the fourth, if we go to very large r, this will not blow up with r. We'll just get this leading order term. So if we have a marginally bound orbit, then the velocity, the potential will go to 0 as r goes to infinity. And if we have a bound orbit, so this is a positive term, then it'll asymptote to this positive value. Yeah, so basically what we want to do is find where v goes to 0, because that will tell us the turning points of the orbit. So the turning points are where basically the radial velocity goes to 0, and we either go from moving inwards to outwards or outwards to inwards. In this expression, this occurs exactly when v equals 0. So in general, we could pick different values of our energy, our angular momentum, then plot v and see what kind of behavior it has. And so we'd have sort of a three-dimensional a function here. So in order to get some intuition for that, let's look at it in a couple limits first. So as I mentioned, we have a bound orbit. That is where e tilde is less than 1, then we let r go to infinity. This r to the fourth term dominates, and so V goes like that, and we'll go to a positive value. So that's at very large distances. Now let's look at what happens at the black hole horizon. So that's for r equal to r plus. So it's easier to look at the equation in this form as opposed to this one. So you recall that at r equals r plus, delta just goes to 0. So this equation simplifies. Yeah, so just that with delta equals to 0. And if we stare at this a little bit, we can notice that we can actually rewrite this as a square. And that means that at the horizon, we know their potential always becomes negative. Yeah, so basically, so far, if we're looking at our velocity, our potential v as a function of r, and for now, let's restrict ourselves to these bound orbits where the e tilde is less than 1. So we know at large r, it's going upwards like r to the 4th. We know that at the black hole horizon, r plus, it's negative. And you notice I can divide this by r. So basically, v over r is going to be a cubic, right? So it's either going to have 1 root or 3 roots as it passes from r plus to r equals infinity. So one possibility is it does something like this. But another possibility is that it does something like this, where it only has 1 root. So this would, so basically, in this case, if we start a particle here, it'll, with inward velocity, it'll move until it hits v equals 0, and it'll turn around and go back outwards until it hits v equals 0 again, and oscillate between these 2 points. Though if we have a particle here, inward velocity, there's nothing to stop it just from falling all the way into the black hole. So basically, we're more interested in this case here, where we have our 3 zeros for our potential that can give us stable bound orbits. So the marginal case between these two different possibilities occurs when basically we have our function just barely, or I should say, just barely touch v equals 0. So if it moved it down more, then we get the 3 roots. If it moves it up a little more, then we get no roots. And so basically, this condition here is that there's some point where the potential is 0 and the derivative of the potential is 0. And does anybody know what kind of orbits these would correspond to? So basically, this will tell us that instantaneously the radial velocity is 0, but also the second time derivative of the radial velocity is also 0. So that would just mean the radius is constant. So what kind of orbit is that? Just shout it out.
Circular orbit.
Circular orbit, thank you. Yeah, so if we want to get these values of radius such that we get these circular orbits, this condition here basically gives us 2 equations, right? And we can just take this expression, set it equal to 0, take the derivative with respect to r, set it equals to 0, and use those 2 equations to solve for E and J. So that's actually going to turn out to be kind of messy. So let me just skip all the algebra and write down the answer. So this is the expression for the energy and angular momentum of a circular orbit, just as a function of the radius of the circular orbit. And one thing that we should point out is that there's kind of a redundancy here in determining the sign of angular momentum, right? So we can choose the particle to have angular momentum that points, for example, in the positive z direction, and then we can, or the negative z direction, and we can also choose the direction of the black hole spin to point in one direction or the other. So if we flip both the spin of the black hole and the sign of the angular momentum of the orbit, then we should get the same answer. So here I'm just restricting to the case where the orbital angular momentum of the particle is positive, but we'll let the sign of the black hole be either positive or negative. Yeah, so let's look at these expressions in a couple different limits. So the first one is when we let the radius of our circular orbit be much larger than m. So we're sort of in the non-relativistic limit. We're far away from our black hole. So in that case, just dropping all the terms that go away, like 1 over r to some higher power, we just get this expression for the energy, and this expression for the angular momentum, and this is just the familiar Newtonian values. So if you take away the rest mass contribution, then you just get the quantity you get for a Newtonian circular orbit once you add the kinetic energy to the potential energy. And same for the angular momentum. But we should also note that these two terms, will blow up when this denominator becomes 0, right? So they can actually get quite large if we. And these denominators are the same, right? So they blow up at the same radius. So if we plot the energy of these circular orbits for large values of r, it's going to go like this: 1 minus m over 2 rc, and then it'll actually reach the minimum, and then it'll start to blow up. And so this let's call this value where it blows up rc min, and we can see that this value is just determined by where this denominator goes to 0. So energy and angular momentum blow up when we have zeros of this equation. So basically, once we reach this lower value of radius, we no longer have geodesics with sort of finite energy. We're actually approaching the sort of limit of moving infinitely, or moving arbitrarily close to the speed of light when we approach this e goes to infinity limit. So let's look at the solution of this equation, a couple different limits. So first of all, if we have a equals 0, then we just drop this term, and we get the lower bound for circular orbits is 3m. And look at the extremal prograde case, so the orbital angular momentum and the spin point in the same direction. In that case, the solution is just the radius is greater than m. And then we can look at the retrograde case with extremal spin. In that case, the lower bound on circular orbits is 4m. And so when the radius actually has these values, that actually corresponds to a photon orbit. That would be followed by a null geodesic. However, not all these circular orbits are actually stable. So it might be true that under small perturbations, they would either fall into the black hole or go out into infinity. To see that, let's recall that so far we've just solved for the cases where v has a 0 and its derivative is 0 at the same point. That means we could either have a case like that, or a case like this. So in this case, we have a stable circular orbit right here. If we perturb it a little bit, it'll just oscillate around this minimum. But we could also be in the case where that point occurs something like this, where we still have a 0 and the derivative is 0. But here, if we have a circular orbiter on this point, if we perturb a little bit outwards, it'll just oscillate back and forth here. And if we perturb a little bit inwards, there's nothing to stop it from falling into the black hole. So some of these circular orbits could be unstable as opposed to being stable. So the marginal case is sort of when these two peaks merge together, and then we have something like this. So yeah, and looking at this plot of the energy versus radius, actually, so we can note that the energy is going to reach some minimum. And then if you continue down in radius, the energy goes up. So that those actually correspond to the unstable orbits, whereas this branch, where above the minimum of the energy, actually correspond to the stable orbits. So define the dividing line between them. What we want to do is solve for where the derivative of the energy as a function of the radius goes to 0. And it's actually turned out to be the same point as where the angular momentum does. Yeah, so what we're looking for is actually has this funny sounding acronym called the ISCO. We want the innermost stable circular orbit. And as we just noted, we can determine the value of the ISCO by solving for where the derivative of the energy of circular orbits with respect to radius goes to 0. Or we could also solve it, for example, by looking for the case where the potential, its first derivative, and its second derivative all vanish. So again, let's see. So I think I didn't erase this expression. But so again, it's a messy algebra, but more or less straightforward. We just take this expression for energy. We take its derivative with respect to the radius. So actually probably easier just to square it first and then take the derivative. And then we set that equal to 0, so we can get rid of the denominator from our differentiated quantity. And after some algebra, I'll just write down the expression we get. Okay, so this expression is actually a quartic in r to the 1/2 power, right? And so, yeah, we can solve quartics using radicals, if you remember your Apple's theorem, but it doesn't look pretty. So let's first just look at it and look at the solution to this in a couple different limiting cases. So the easiest one, of course, is just when the spin of the black hole is 0, then we drop these two terms, and we can see that the ISCO is just equal to the radius of the ISCO is just 6m. And perhaps you already learned that in your previous GR course for Schwarzschild. Then we can look at the extremal case with prograde motion. So in that case, the ISCO turns out to be m. So we can check that here. So we're just going to get 1 minus 6, and then we'll get 8 here, and then we'll get 3. So that does any d equals 0. And then consider the retrograde case. And the answer there turns out to be 9m. So check that again. So we get 9 squared is 81. And then 6 times 9 is 54. And 8 times, or yeah, minus 8 times 3 is 24. And then minus 3. And if we sum that up, we indeed get 0. So we can see that the ISCO sort of monotonic, or let's just say, yeah, so these are the three sort of limiting cases. I can go ahead and write down the general expression. And so here, I'm introducing this quantity capital A, which is this. And also this quantity B, which is given by this. So not too bad for being a quartic solution. And so we can check that indeed if we plug in these values, this equation is satisfied. And you can also note that the ISCO is actually a monotonically decreasing function of the spin. So as we go from minus, or A equals minus m to A equals m, the ISCO moves in continuously, going from 9m to 1m. And so this is the innermost radius, which we have stable circular orbits, and then in between the ISCO and this value of R min, which, okay, yeah, here we go, which comes from the solution of this equation. We have still circular orbits, but they're unstable. Yeah, and so in the tutorial this afternoon, you'll actually explore what happens when you look at perturbations of unstable orbits and get this very interesting behavior called zoom whirl. So I'll leave it to you this afternoon to discover why it has that name, zoom whirl. Yeah, so any questions so far? Okay, so deriving those expressions for the ISCO was a little bit messy, and I basically skipped over the even more messy parts of the algebra. But I did think it was important to sort of write down these expressions and for you to have these numbers in mind, because they actually sort of give you intuition into a lot of sort of astrophysically relevant situations around black holes. And they can also help you understand not even the motion of test particles around black holes, but actually even massive systems around black holes, like two black holes merging. So to sort of put this knowledge to use in our last 10 minutes, so let's imagine that you have a small object that's in a circular orbiter on a black hole, and it's emitting gravitational waves, so it's losing orbital energy, and that means the radius of the orbit will be shrinking. But we'll imagine the object is very small, so this loss of energy due to gravitational waves happens very slowly. So we can think of this orbit as quasi-circular. So say we have our black hole, and then we have some particle here. It's going around in a circular orbit, and it's very slowly losing energy. So the orbit is shrinking. And it's getting closer and closer to the black hole. And then at some point, it'll start to undergo what's called a plunge, and then very rapidly fall into a black hole. So can anyone tell me at what radius we expect the plunge to happen for a small object orbiting around a black hole? Feel free to raise your hand, even if it's obvious. The ISCO, yeah. This allows us to say that if we have let's say we have an orbit that points in one direction, and then our black hole has spin. So what do we expect the plunge to happen sooner or later for a black hole where the spin is anti-aligned with the particle's orbital angular momentum? So retrograde motion, will the plunge happen sooner or later compared to the non-spinning case? Anybody?
Sooner.
Yep, sooner. It'll happen sooner. And then if we're in the opposite case, where the black hole spin is aligned with the orbital motion, then this plunge will happen later. So we'll get more cycles. So that these geodesics sort of only technically apply to sort of small test bodies, but let's sort of stretch the limits and see if we can use this intuition for the non-extreme mass ratio case. So if you remember, so let's consider instead two black holes merging and producing a gravitational wave signal that's, for example, seen by LIGO. So you probably remember these very nice pictures that LIGO has put out where they show you a sonogram, which basically is time and frequency. And then they show you the basically the energy in the gravitational wave in this time frequency plane. So you get a signal that sort of is increasing frequency as a function of time, and all of a sudden has this chirp, and then it goes to a merger. And then the signal ends here. So let's say you have two different binary black hole signals, and at sort of early times and small frequencies, they look similar. But if you compare one to the other, so let's call this case 1. The other case follows at early times, and then as time goes on, it undergoes this sort of merger at a later time and extending to higher frequencies. So if we could say that the masses of the two black holes are roughly comparable for the two different systems, what can we say about the spins of these two cases compared to each other? So
the second one went further in, right?
Yeah, so it has more cycles.
Spin is bigger and it's more,
Yeah, so this would indicate to us that the second case has more spin that's aligned with the orbital angular momentum. So you get more cycles of the gravitational wave, and then the merger happens at a higher frequency. Yeah, and so this fact is also this effect for binary black hole mergers, that when you have spin aligned with the orbital angular momentum, you get more cycles, and the merger happens at a higher frequency, has this name. It's called the orbital hang-up effect. But you don't really need a fancy name for it. It's really just something that you can sort of intuit already from the geodesic equation, just from the fact that the ISCO moves in when you have prograde motion. And this is also, of course, related to the fact that when you're observing gravitational waves with an instrument like LIGO, the part of the black hole spin that you're primarily sensitive to is actually the component of the black hole spin that's aligned with the orbital angular momentum. To see the effect of the spin that's sort of perpendicular to the orbital angular momentum is harder, and you have to look for these precession effects that can show up when we have these longer waveforms. And so besides being important for gravitational wave observations, the ISCO is also important for sort of electromagnetic observations of accreting black hole systems. So let's say you have a black hole and it has an accretion disk. So here's kind of the side angle view of the accretion disk. Let's say we have a black hole, has some spin that points in this direction here. And then the top-down view will look like this. And so from these accreting black hole systems, they produce electromagnetic radiation, for example, the X-rays that we can observe with telescopes. And we can use these observations to try to infer what the black hole spin is, and then sort of take a census of our observable universe and see what kinds of black hole spins there are. So of course, you can't see the black hole directly. You just see the X-rays coming from this accretion disk here. But the ISCO basically sets exactly how far the accretion disk will extend towards the black hole. So if we have spin, if we have large spin, then the accretion disk can extend down further, closer to the black hole, deeper in the potential well. Whereas if we have no spin, then this ISCO will be at larger radius. Yep, so any questions about that?
I have a question.
Yeah.
Once I heard that most of the templates that LIGO makes for the binary merger are circular, like it's kind of like circular merger. Is that true?
Yeah, they're mostly quasi-circular.
Yeah.
Yeah.
Why is that? Because it's most probable that that will happen, or?
Yeah. So it's the reason for that is so you can start with a system that is not circular but has some large eccentricity.
Yeah.
But we imagine for most of these systems, basically they start as a bound system at very large separations. So they're going to take a very long time to actually lose energy to gravitational waves to get closer and closer and then finally merge. And I think you actually derived this in a homework problem in week 3. But it actually turns out that gravitational waves are very good at sort of circularizing orbits. If you start with some eccentricity and then emit gravitational waves, the energy and angular momentum that are carried away by those gravitational waves will actually work to reduce the eccentricity. So as long as you start far enough away, by the time they get close enough to emit strong enough gravitational waves that LIGO could see, they would be essentially quasi-circular.
Okay, great.
Yeah. There might be some sort of more exotic systems where you're not sort of forming black holes in or neutron stars like already in bound systems, but you start with them separated and then they form a binary in dense stellar environments like globular clusters or things like that. And so there, if they can sort of form binary with a small enough periapse value, basically, then they might merge with some non-negligible eccentricity. That's considered a little bit more exotic scenario. Okay, so if there are no other questions, I think we'll call it a day. And yeah, come to the tutorial and we'll find out what Zoom world orbits are.